Hello students, welcome back to Akshar IIT classes and I am your chemistry faculty S. Mohan. Students, in the last class we are discussing about the atomic structure and electromagnetic radiations, right? So today we are going to discuss about a new topic called the black body radiation and also some important concept called the Planck's quantum theory of radiation, right? So now let us see black body radiation. Do you know what is meant by the black body radiation? See here, generally when we take one object, for example, if I have one object, see this is one object, right? This object I am placing in the radiation, like for example in presence of sunlight. So what happens here? The sunlight rays are falling on this object, right? After falling the rays, some of the rays means some of the heat of the rays, energy of the rays is absorbed by this object, right? And some part of the rays will be reflected back. Is this clear? So always most of the object in the nature are that whenever the radiations falls on it, some of the radiations will be absorbed and some of the radiations will be emitted back, right? But here the black body is that it is an ideal body. Whatever the radiations falls on it, it absorbs all the radiations which are falling on it and all the radiations emits also. So the meaning is what? Black body is not only a perfect observer but also a perfect radiator. So can you see here now? Here an ideal body which is a perfect observer and also perfect emitter of radiation. What's the meaning of this one? Whatever the radiations falling on this object, that absorbs all the radiations and it also emits all the radiations, right? So this type of body is called as a black body, okay? And the radiations emitted by such a black body is called black body radiations, right? So the black body radiations was not explained by the classical electromagnetic theory. So here you can see a classical electromagnetic theory. So the black body radiations cannot be explained by using the classical electromagnetic theory. So to explain that, Max Planck in the 1901 proposed a new theory called as a Planck's quantum theory of radiation. Okay, so you see Planck's quantum theory. Who proposed it? Max Planck. When? In the year 1901. For what purpose? To explain the black body radiation. Clear to you? Chalo. Any doubt in this topic? Let's go to the next topic. Now, what actually the black quantum theory of radiations explains? See here, according to the electromagnetic radiations, in the last class we discussed that electromagnetic radiations are the radiations which are associated with electric and magnetic fields and they travel in the form of a wave, right? So, according to Huygens and this one, Max Planck, so here the electromagnetic radiations consist of they travel in the form of a wave, okay? They possess what? A wave nature, right? But here Planck said that energy will be emitted or absorbed not continuously but in the form of a small packets called quantum. The meaning is what? For example, if here it is a sun. So students, here this is a sun, right? Here there is an earth, right? Now from this sun the radiations are coming to the earth and it's falling on the earth. Is this clear to you? So here it looks like the radiations are continuously traveling and from the sun and reaching to the earth. But Planck's quantum theory, what it states is energy neither be absorbed or nor be emitted continuously but in the form of a small packets called the quanta. The meaning is what? Here the radiations cannot continuously emitted from the sun but it is emitted discretely. Discretely means what? Like this, okay? So like this they are emitted discretely and these discreted particles which are consist of energy, we can say that energy bundles, they reach to the earth, right? So any object which emits out the energy or which absorbs energy does not takes place continuously, but it takes place in the form of a small packets called quanta. So the first packet is the first point is here. Radiant energy emitted or observed is not continuously, but discontinuously in the form of a small packet called a quanta. So the small packet is what? It's a packet of energy. It's a packet of energy. So this is called a quantum, right? And second point is the most important point. The energy of the quantum is directly proportional to its frequency. The energy of the quanta is directly proportional to its frequency. So in the last class we discussed about the electromagnetic radiations. In that some terminologies we discussed, like wavelength, frequency, velocity, time period. This all we discussed, right? So here energy of the quanta is directly proportional to the frequency. So how can we write here? Energy, okay, is proportional to, this is a symbol of what? Is proportional to the frequency, okay, and energy is denoted by E is proportional to the frequency is denoted by nu. This we discussed in the last class, right? So here the amount of energy associated with quantum of radiation is proportional to frequency. Proportional to means what? Here if one quantity increases, other quantity also increases. If both the quantities are increasing, then we can say that proportionality, right? So directly proportional is there and inversely proportional is there. So I think you might have studied in the mathematics. Inversely proportional means what? If there are two quantities, if one quantity increases, then other quantity decreases. If other quantity increases, the first quantity decreases. So these are called inversely proportional. What they are called? Inversely proportional. But here it is what? Directly proportional. So what's the directly proportional? If two quantities are there, if one quantity increases, then the other quantity also increases. Clear to you? So here the energy of radiation is directly proportional to frequency. The meaning is what? As the frequency increases, energy also increases. Okay? As the frequency increases, energy also increases. So E is directly proportional to nu, right? So E is directly proportional to nu. When you remove a proportionality constant, when you remove the proportionality constant, proportionality sign, you get one constant. Okay? Whenever you remove proportionality sign, you get one constant, right? So here, when you are removing this proportionality sign, then what happens here? This becomes is equal to, and a constant will join there, right? Yeah, that constant is H. Clear to you? So E is proportional to nu, and when you remove this proportionality sign, then it will be equated with one constant. Here the constant is H. Is this clear? So E is directly proportional to nu, or E is equal to H nu, where H is called proportionality constant or Planck's constant. Proportionality constant or Planck's constant. Clear to you? Why it's called Planck's constant? Because this theory was proposed by the Max Planck, right? So here E is equal to H nu, right? So here for every constant there will be one value. For every constant there will be one value, and that value here is 6.625 into 10 to the power of minus 34 joules second. Okay, so see, where H is a constant known as a Planck's constant, it is equal to 6.625 into 10 to the power of minus 34 joules second. Okay, so here student, very important question, it may be asked you, what is the unit of Planck's constant? So the Planck's constant unit is joule second. What is the constant unit of the Planck's constant? That is joule second, and its value is 6.625 into 10 to the power of minus 34 joules. So it's a very important value, because to solve a numerical, then you need to remember this value. These values will not be given in the examination. Clear? Right. Now, the energy of the quantum, okay, of the photon in terms of wavelength and light. So already we discussed in the last class, the electromagnetic radiation, the speed of light c is equal to nu lambda. Did you remember? Okay, I give the formula that c is equal to nu lambda, right? what is the c? C is the speed of light. C is what? Speed of light. And nu is what? Nu is a frequency and wavelength is lambda, right? If c is equal to nu lambda, then this lambda you get it this side. So this becomes what? C by lambda is equal to nu. So nu is equal to what we can write here? C by lambda, right? What is nu? Frequency. So frequency can be written as C by lambda, where C is the speed of light and lambda is the wavelength, right? Now what we have a formula here, E is equal to h nu, okay? E is equal to h nu. So now what I am doing here, you see, E is equal to h and nu is it. But here from this equation, what I have, nu is equal to C by lambda, okay? So in the place of nu, I substitute this one. So I can write C by lambda. So E is equal to hc by lambda. This is also one of the formulas. So here E is equal to hc by lambda. Clear to you? Any doubt? So once again this I am going to explain you. So Planck's quantum theory, what it states, the energy, emission of energy or absorption of energy does not take place continuously, but it takes place in the form of a small packets of energy called quanta. That's the first point, right? What is the second point? The energy of the quanta is directly proportional to its frequency. In short, what we can write? E is proportional to nu. When you remove the proportionality sign, we get one constant, and that constant is h here. So we can write the equation E is equal to h nu, where h is called Planck's constant, and every constant will have some value, and here the value of Planck's constant is 6.625 into 10 to the power of minus 34 joule second. So here the SI unit of Planck's constant is joule second. Clear? Next word, and so E is equal to h nu. In terms of, you want to write the wavelength, in terms of wavelength, the same formula can be written as E is equal to h nu can be written as E is equal to hc by lambda. Why? Because frequency is equal to C by lambda. This already we discussed in the last class. Clear? Chalo. Now come to the last and final point here. Here the body can emit or absorb the energy in terms of, okay, in terms of 1 nu, 1 h nu or 2 h nu or 3 h nu or 4 h nu or n h nu. The meaning is what? The energy of the quanta is quantized. Okay, what is the quantized? Quantized means what? Integral multiples or multiple integers. Okay, so the meaning is what? For example, some, okay, here this is a quanta. This quanta have an energy of h nu. So E is equal to h nu. Or some another quanta is there. Its energy may be E is equal to 2h nu. Okay, or E is there one more energy and it may be 3h nu, right? But it can't be, okay, the energy can't be like 1.5 h nu or 2.75 h nu or 3 by 2 h nu. So like this. Is this clear to you? So always the energy of the quanta is multiple integrals. Okay, multiple integrals of h nu. Multiple integrals of h nu means what? Maybe 1 h nu, maybe 2 h nu, maybe 3 h nu, maybe 4 h nu. So, but maybe n h nu, wherein is a integer. Wherein is what? Integer. Clear to you? So that means now see here, a body can observe, emit or observe energy integral multiples of quantum. Integral means multiples means what? The multiples of integers. What are the integers? 0, 1, 2, 3, 4 and so on are called 1, 2, 3, 4 is called integers, right? So always the energy is given by E is equal to h nu. E is equal to what? H nu. So it may be 1 h nu, it may be 2 h nu, it may be 3 h nu, but it can't be 1 h nu, 1.5 h nu or 2.75 h nu or 3 by 2 h nu. Is this clear to you? So this is called the, now this means that the body can emit or absorb the energy in terms of here h nu, 2 h nu, 3 h nu 4h but cannot emit or absorb the energy in the fractional values. Okay, in the fractional values. Clear to you? So that's all about the Planck's quantum theory of radiation, right? Now next come to the photoelectric effect. So see students, here the next topic is photoelectric effect. Can you say what is mean the photo? What is mean the photo? Photo means light. What is mean the photo? Photo means light. You might have studied in the biology about photosynthesis. What is mean the photosynthesis? So plants can prepare their food. Synthesize. Synthesize means what? Prepare. Plants can prepare their food with the help of the sunlight. With the help of the sunlight. This sunlight is called photo. Is this clear to you? In science, photo means what? Light. So the photo, the meaning is light. Electric effect. Electric means what? Electrical energy. So electric means what? Electrical energy. Electrical energy. So photoelectric effect means what? A process in which light energy can be converted into electrical energy. What is the photoelectric effect? The process in which light energy can be converted into electrical energy. This phenomena is called photoelectric effect. Clear? Very simple definition. So photoelectric effect means what? The phenomena in which light energy is converted into electrical energy, right? Now let us see how light energy can be converted into electrical energy, right? So now here see students, here what we do is we take one metal surface, okay? So we are taking one metal surface. So here you can see this is the metal surface, okay? This is the metal surface, and normally photoelectric effect, to show the photoelectric effect, we take the alkali metals. Which metals? Alkali metals. Mostly we take alkali metals. Why? Because the ionization energy of the alkali metals is very less. Means what? A very less amount of energy is required to plug the electrons or to remove the electrons from the metal surface. Clear to you? So that's what we take the alkali metals. In that also, mostly we take the cesium. Which element we take? Cesium. Okay, cesium. So we can take the element called the cesium. So see students, here try to understand here. This is a metal surface. Okay, and this is which metal here it is I am taking? Cesium I am taking. Why? Because the ionization energy of the cesium is very less. Means what? Here to remove the electron, it's very easy to remove the electron from the cesium, right? So here in this metal plate, what we are doing is here, this red color line is, so this is the, okay, we are supplying the energy, means the radiations are falling on this metal surface, right? When the energy is falling on the metal surface, means energy is falling in the terms of a quanta. In terms of what? Quanta. So this quanta is falling on the metal surface. Some part of the energy of that quanta is utilized by this metal surface to remove the electrons, means to take out the electrons, right? So these electrons, okay, some part of the energy is utilized to overcome the force of attraction, and the electrons come out of the metal surface, and remaining part of energy is utilized to provide the kinetic energy, So whenever the light falls on it, whenever the light falls on the cesium metal, then the energy of the light is taken by the electron, and electrons come out, okay, and they can conduct the electricity. So here you can see students, here Einstein explained the photoelectric effect on the basis of quantum theory. On the basis of what? Quantum theory. So see, it is observed that electrons are ejected from the surface of certain metals when the light falls on it. Did you understand, students? So for example, you see this is some metal surface. Okay, for example, I am taking the cesium metal. Now I am exposing this to sunlight. So when the sunlight falls on it, so the energy of the sunlight makes to take out the electrons from this cesium metal, right? So this is known as photoelectric effect. What it's called as a photoelectric effect. Thus, photoelectric effect may be defined as the phenomena of ejection of electrons from the surface of metal when the light of suitable frequency strikes to this. Okay, so when I'm placing this metal, so whenever the suitable frequency light is falling on it, so this makes to eject the electrons from it. So this phenomena is called as a photoelectric effect. Clear to you know photoelectric effect? So photo means what? Light, electrical energy, effect. So the phenomena in which light energy can be converted into electrical energy is called photoelectric effect. Okay, right. Now see some important observations about the photoelectric effect. Now students here see, for example, here this is on metal surface. This is metal surface. Now this metal surface I am exposing to the light. For example, you see here there are lights are there, right? So these lights are there, I am exposing to this light. So now from this light is a form of energy. So this light is falling on this surface, right? Now can the electrons, does the electrons emit from this one? Means may or may not. Why? Because the energy which is releasing from this electric lamp may not be sufficient to take out the electrons. Okay, so the frequency of energy may not be sufficient, okay, to take out the electrons. So what can I do if you want me to take the electrons from this one? I need to apply the energy whose frequency is little more. Clear to you? So the meaning is, just now we discussed that in the Planck's quantity. What we discussed, energy of the quanta is directly proportional to its frequency. So to take out the electrons from metal, it requires certain amount of energy. So that energy may not be present in this electric lamp. Is this clear to you? So due to this, what happens? This is exposed to the light and light radiations are falling on it, but still the electrons are not emitting from this surface. Why? The energy may not be sufficient. Means what? To eject the electron from the particular surface of metal, then it requires certain frequency. Okay, it requires certain frequency. So that's the first point, student here. So here for a particular metal, there exists a threshold frequency. Threshold frequency means what? The minimum frequency that required to take out the electrons from the metal surface is called threshold frequency. What is the threshold frequency? The minimum frequency that required to take the electrons from the metal surface is called the threshold frequency. So here for a particular metal, there exists a threshold frequency such that at frequencies below the threshold, no electrons are emitted. Okay, means the particular amount of energy radiations, particular amount of radiations with a particular frequency is required to eject the electrons. If the frequency is below, okay, then threshold frequency, then no electrons can be ejected. Clear to you? So that's the first point. Now second point is what? The maximum kinetic energy of the photoelectrons is directly proportional to the frequency. So just now I told you that whenever the light falls on it, when the radiations falls on it, then certain part means a certain amount, some part of energy is utilized to pluck the electrons. Pluck means what? To remove the electrons, okay, from their orbits, and remaining part of energy provides the kinetic energy. Remaining part of energy provides the kinetic energy. Kinetic energy means what? Due to kinetic energy, the electrons will be, okay, traveling, means they are moving, okay. So this motion in the electrons will be given by the kinetic energy, right? So this kinetic energy provided by the what? The radiation. Is this clear to you? So the kinetic energy of the electrons is also directly proportional to the frequency. Means as the frequency increases, the kinetic energy also increases. So you can see here the maximum kinetic energy of the photoelectrons is directly proportional to the frequency, okay, of the incident radiations, but it is independent to its intensity of light. Intensity means what? The energy per unit area is called as the intensity, right? Now, the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation, but does not on the frequency. Now, how many number of electrons are releasing from this metal? How many number? The number of electrons ejected is directly proportional to the intensity of light. Clear? So, this so this is about the Planck's quantum theory and the photoelectric effect. And photoelectric equation is given by like this. Okay, kinetic energy is equal to h nu minus h nu dash. H nu is what? The total energy. Okay, total. Just now I told you, know. So the amount of energy which is coming from the radiation of light. Okay, radiation of coming light, that is given as E. In that, some part of energy is utilized to take out the electrons. That energy is called work function. What is called? Work function. And remaining part of the energy is utilized for provide the kinetic energy. So E is equal to W. W means what? The minimum amount of energy required to remove the electron. Okay. Okay. So here this is the total energy from the radiation. In that, some part of energy is used to remove the electrons, and remaining part of the energy provides the kinetic energy. So here this amount of energy, okay, amount of energy which is releasing from the, which is present in the quanta is given by h nu, right? H nu is equal to some part of energy is utilized to remove the electron. So that is denoted by h nu naught, plus this is the kinetic energy. Now what you do, kinetic energy keep there only, and this h nu naught bring this side, right? So then what happens here? H nu, okay, this is coming here towards the left side, so this becomes minus h nu naught is equal to kinetic energy. Is equal to what? Kinetic energy. So therefore, what we can write the kinetic energy? Kinetic energy is equal to h nu minus h nu naught, h nu minus h nu naught. Clear? So this is about the photoelectric effect. Any doubt? Chalo. Now let's see the next topic. Over. So now let's solve some numericals. So this is a practice sheet 5. First, let's see the concept based questions. Which of the following relates to photon both as a wave motion and as a stream of particles? First option, interference. Second option, E is equal to mc square. Third one is diffraction, and fourth one is E is equal to h nu. What's the answer? E is equal to h nu according to Planck's quantum theory. So the option is 4. Second one, the photoelectric emission from a surface starts only when the light incident upon the surface has a certain minimum. So to take out the electron, I said that certain minimum, what is required? Intensity, wavelength, frequency and velocity. What's the option? Frequency, minimum frequency, which is called as a threshold frequency, I told you, right? Next, a beam of light falls on the cesium, just now I discussed you, okay? Cesium metal cause electron emission. This property is known as what's here? Paramagnetism, fluorescence, phosphorescence and photoelectric effect. What is the answer? Photoelectric effect, because the light, photo means what? Light, electric means what? Electricity. So photoelectric effect. Next, kinetic energy of the photoelectrons is independent. Kinetic energy of the photoelectrons are independent of what? Intensity. Just you go back to this slide so you can see here. Now, so here you can see here the kinetic energy, okay, of the electric direct frequency, and it is independent to the intensity. Clear to you? Right. Next, the value of Planck's constant. What is the value of Planck's constant? 6.625 into 10 to the power of minus 34 joules second. So what's the option here? Here, second option, 6.625 into 10 to the power of minus 34 joules second, right? Next, the ratio of energy to frequency of electromagnetic radiation is here, the ratio of energy to frequency. So here we have that what just now I told you that according to Planck's theory, see, E is equal to h nu. E is equal to h nu. So E is the energy, nu is the frequency. So energy to frequency, so what you do now, bring here nu. So this becomes what? E by nu is equal to h. So they are asking now what is E by nu. So the ratio of energy of frequency of electromagnetic radiations, what is that? Kinetic energy, electrical energy, chemical energy, Planck's constant. So here it is h is Planck's constant. So the answer is 4. Clear? Any doubt? Okay. Now let's see in photoelectric effect. In the photoelectric effect, the number of photoelectrons, the number, you see here, this is very important. The number of photoelectrons are emitted is proportional to what? Intensity of light. Intensity of light. See in the previous slide, let us see here. So here I told you. See here, the number of photoelectric emission per second is directly proportional to intensity of light. So the answer is what? Intensity of light. Next, the kinetic energy of the ejected electrons in the photoelectric effect is directly proportional to frequency. So what is the answer here? First option, directly proportional to the frequency of incident radiation. Next, photoelectric effect is not observed in the case of. So students, I said you that photoelectric effect mostly it is observed in alkali metals. What are the alkali metals? Except the hydrogen, remaining first group elements are comes under the alkali metals. In the periodic table, if you see, the first group consists of hydrogen, lithium, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. The first element is what? Hydrogen. If you remove the hydrogen, except the hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. These are called alkali metals. Now you see here, which is not there telling. Okay. So potassium it is there, just now I written. What are the elements I have written? So remember here, except the hydrogen. So hydrogen is not there. Lithium, sodium, potassium, rubidium, cesium. These are the first group elements. So mostly we can see the photoelectric effect in these elements. But what the question is, photoelectric effect is not observed. So which of this element is not a part of this one? See here now. So here potassium, yeah, potassium is there. Rubidium, yeah, rubidium is also there. Cesium, cesium also there. In this series, which element is not there? Magnesium is not there. So the answer is magnesium. Clear to you? Now the last and final one, as the frequency of the light increases, the momentum of the photon increases because kinetic energy increases. As the frequency increases, kinetic energy increases. Kinetic energy formula is what? Half mv square. So see students here, kinetic energy. So kinetic energy formula is what? Half mv square. Now can I write this mv square as half into mv into v? Can I write this now? So here mv is a momentum. Mv is what? Momentum. So kinetic energy is directly proportional to frequency. Okay. So as the frequency increases, kinetic energy increases. As the kinetic energy is increasing means what? The momentum also increases. So the answer is increases. Clear students? So that's all for today. So this is with this we completed the fifth synopsis, that is Planck's quantum theory and black body radiations. Okay. So we'll have a next class. We'll meet. Till that, you take care of yourself. Bye.